Hi, everyone. Welcome to our session today. My name is Joey Burba. I'm one of the AWS Solutions Architects supporting Netflix. And we're going to spend the next hour together learning how Netflix has scaled container networking on their internal platform called Titus, which today is heavily influenced by the Kubernetes API spec. Now, containers have lots of advantages. They're really portable. It's very easy to go from dev to test to production. Fairly easy. They're also very lightweight. They share a common base operating system, so we tend to just package our application code and dependencies in our container so they can come up and down very, very quickly and go down just as quickly. We can also put lots and lots of containers on a single server and make really efficient use of resources like CPUs and GPUs and memory. Now, that being said, they also introduce a lot of challenges around networking. For example, how do we provide IP addresses to hundreds of containers on a single node? How do we ensure these containers can access services and we can access them? And how do we do this performantly, efficiently, and securely at Netflix scale? So today we invited Hechao Li from Netflix. She's going to walk us through some of the challenges they face scaling container networking. And she's a senior software engineer at Netflix. And she's put together a great session for us. You can have a lot of fun. So if you could, please welcome Hechao Li to the stage.
Hello, everyone. My name is Hechao, and I'm going to talk about how Netflix efficiently configure container networking for millions of containers running in our production. So today's agenda is very simple. First, we talk about containers. Next, we talk about networking. Finally, we talk about container networking. Simple like that. Because we will spend the majority of our time on the container networking challenges, how we solve them. So I would like to make sure, first, everyone knows why we have to go through all the troubles to solve this problem. So number one question, containers. Why? Why do we even need containers? Quick show of hands, how many of you use containers to run your application, not to store your food? Okay, the majority of the room, that's nice. Even for those who didn't raise your hand, I'm pretty sure your business runs just fine without containers. In fact, Netflix used to run everything on EC2 without containers for years. But eventually, we decided to migrate to containers. And why is that? Number one reason for portability and consistency. What are you supposed to say as a software engineer when some people tell you, hey, your application, your software fail in production? So what do you want to say to that? So I'm going to guess you will say, hey, look, it works on my machine. So if you have never said this, you are not a qualified software engineer. By using containers, you can ensure your application runs consistently in your dev, your testing, your production environment, so that you can avoid this kind of it works on my machine problem. Reason number two is for faster deployment, because containers, not like VMs, that you need to wait for the full initialization of your operating system. So you can deploy containers fairly quickly. And it is especially useful for your CI/CD pipelines. You can quickly verify things and iterate. Last but not least, cost and efficiency. I'm pretty sure you have heard the word efficiency a lot in the past maybe 2-3 years. So we all run our application, our business on AWS cloud, and we would like to make sure our money is worth spending on AWS. We want to make sure all of our resources is efficiently used. And how is container going to help with that? Let's take a look at an example. So you run your business on AWS cloud, you have developers developing software. So say a developer, Alice, comes with her super cool software, and she wants to run this application on AWS cloud. Let's say we run it on EC2. Then the first question Alice has to answer is, what type of EC2 machine I should use to deploy my software? Well, I don't know. Alice thinks I'm not really familiar with AWS. Let's say I'm just going to use a general purpose M5 type. And in terms of size, well, I don't want the smallest. I may need more resources. I also don't want to use a larger one because I may spend more money. So I'm just going to choose the second largest, M5, extra large, with 4 CPUs. That's enough for me at this moment. I'm going to deploy my application there. Later, another developer, Bob, comes with the same requirement. Bob also wants to deploy his software onto the cloud. Now he has to answer the same question: what type of EC2 machine should I use? Well, I don't know either. Bob thinks, well, I will just see, it looks like Alice knows her stuff. I will just copy whatever Alice is doing here. I'm also going to start an M5 extra large with 4 CPUs. After all, we are all software engineers. We are all guilty of stealing other people's code. So Bob just copies the same configuration and does the deployment. So on and so forth. When Charlie comes, Daisy comes, they just copy each other's code and they do the same deployment. Now, let's assume each of their application is not very CPU intensive. They only use 1 CPU at runtime. So if we look at this setup, we are paying for 16 CPUs on 4 EC2 instances, but our CPU utilization is only 25%. Now, let's imagine you have a magic box that can help you do the deployment. And then same situation, Alice as a developer comes, and then she wants to deploy the application. Now, she asks this magic box, please deploy this for me. And the magic box looks at the setup and find no EC2 instance at the moment. So the magic box is going to start a M5 extra large for CPUs and then do the deployment. Later, another developer, Bob, comes with his software, and the box looks at the current setup and finds, okay, I already have 1 M5 extra large. The utilization is only 25%, and it can run another application, so I'm just going to deploy this Bob's application onto the same EC2 machine. And so on and so forth. For Charlie, for Daisy, they will just have their software deployed without having to worry about the EC2 instance type. And now, if we look at this setup, we are only using 2 M5 extra large. We are paying for 8 CPUs, but the utilization is 50%. And so money saved and efficiency improved. So now the question is, what is this magic box? The magic box is a container management system, and at Netflix, we call it Titus. Titus is our multi-tenant container orchestration system with tight AWS integration. So around the time we started migrating our services to containers, because of the scale of Netflix, there was no off-the-shelf offering that could just work for us, for our scale, for our traffic. So we decided to build everything ourselves. Because today's topic is not about container management itself, so for the purpose of this talk, you only need to know Titus is this magic box that can help you deploy your application as containers on EC2 instances. So containers, they have this interesting relationship. They want isolation. So one important feature of container is isolation. Even if they share the same physical space, they want to be isolated from each other. And at the same time, they want to communicate with each other. So it's like me and my family. We want isolation, but we need communication. So that's why you need networking setup for your containers. And how do we do that? So before going into designing the container networking, let's review how the network function in general. How is the data transmitted through the network? If you have ever taken any network classes at school, you may remember the packets will go through layers, and there is a theoretical 7-layer OSI model for the networking. I'm not going into that. That's too theoretical. I'm going to talk about a more practical TCP/IP model, the 5 layers. So at the application layer, your application developer has some data to be sent out. And at this layer, you deal with protocols like HTTP, HTTPS. And once the data is ready, you do some system calls, and then it goes to the next layer, the transport layer. And you have TCP or UDP protocol at this layer. I'm going to use TCP as an example. So a TCP header will be added to your data with some port number that's used to identify the upper level application. This is sent from and to. And next, the packet or the frame will arrive at internet layer, and at this layer, an IP header is added. The IP header includes the IP addresses, the source and destination IP addresses that you use to identify nodes on the network. Next, the IP packet will arrive at what we call network interface layer. At this layer, you deal with Ethernet protocol, and you use MAC address or hardware address to identify nodes on your local area network. Eventually, all those data, it will arrive at the physical network on the wires as bits, zeros and ones, and be transmitted to the destination. And on the destination, the packet will go all the way up from bottom to top and then be unpackaged and received by the destination application. So those are all the 5 layers we need in order for the data to be transmitted through the network. So who is responsible for which layer? Obviously, the application developers, Alice and Bob, they are responsible for the application layer. And the operating system will take care of the transport layer. For example, you do some Linux system call, then the Linux TCP stack is going to handle TCP protocol for you. If you run your application on EC2 instances, then the Amazon EC2 service will take care of the next 2 layers. It's going to attach Elastic Network Interface, or ENI, onto this EC2 machine, and then assign some IP addresses to it. Then those 2 layers are configured, and your EC2 instance will have network connectivity. But now we are migrating stuff from EC2 to containers. Now it's the job of the container management system, or Titus in this case, to configure those 2 layers, layer 2 and layer 3. So to summarize, the goal of Titus is to configure the internet layer and network interface layer for each container, or in other words, can configure the ENI, Elastic Network Interface, and IP addresses. Okay, now with that in our mind, let's start designing a container networking. So before we go into the actual design, we need to understand what are the requirements of the Netflix container networking. So requirements number 1, so now we are migrating applications to containers. Then I will go to an application developer. I ask Alice, hey Alice, what is your requirement if we want to migrate you to containers? Guess what Alice will say? Well, I bet Alice will say, I don't care. I don't care about containers. I don't care about networking. As long as my application, my services runs in the cloud, I don't care where you migrate them into. That's fair. As application developers, they shouldn't be worrying about infrastructure, and that's a job of infrastructure engineers like me. So actually, Alice already told me her first requirement. That's we want the containers to run like EC2 VMs because it's already working on the cloud. So we don't want any friction in developer experience. For example, even if the container networking is 1 layer of abstraction on top of EC2, we don't want any netting, bridging, translation mechanism there. We want each container to have 1 IP in the network, just like a EC2 VM. They can just use that IP to access SSH into those containers, do whatever they like, just as before when they run everything on EC2. And currently on EC2, we use security groups as the security mechanism to control the traffic going in or going out of all the EC2 instances. So we want to use the same mechanism for containers. Requirement number 2 is, I mentioned before, isolation is important for containers. And the isolation is twofold in this case. First, data plane isolation. We mentioned all of them, they run on the same EC2 instances. They share physical resources, but they want to be isolated from each other. They don't want to see each other's network traffic. And this can be easily achieved by using Linux network namespaces. So they won't be seeing each other's traffic. But there is more, and I will mention later. Another requirement for isolation is account level isolation. At Netflix, some teams, they have those requirements that need to run their application in a separate account, different from the production account where most of the people use. And they want their application to use resources, both compute and networking resources in those different accounts. Last but not least, the low latency requirement. So one feature I mentioned about container is faster deployment. So we want to make sure when you start a container, it takes very little time to set it up. So, and the setup includes network setup. I have ever seen like very short-lived containers in our environment. A container, it can launch, run for say 5 seconds, and in those 5 seconds, they need to use the network, and then they go away. But we need to set up the network for such a short-lived container. We want to make sure we don't take say 5 minutes to configure the network. That would be unreasonable. And more than that, sometimes we have bursty workloads. For example, let's assume everyone in this room, suddenly you all decide the talks are boring, I'm not going to listen to any of those, I'm going to switch to watch Netflix, watch my favorite show on Netflix. Then all of you may start a microburst in our environment. We may need to launch hundreds of containers to serve your needs. Then even in those cases, when there are bursty workloads, we want to make sure the container setup time, network setup time is still within a reasonable range. All right, with all the requirements, all the 3 requirements in our mind, let's dive into the design of our system. So if you remember, our goal is to configure a NIC, or ENI, Elastic Network Interface, and IP for each container. We have several options, and then let's take a look at the EC2 network first. In an EC2 network, you have an account, you have run VPC, Virtual Private Cloud Init. In each VPC, you have a subnet, and in the subnet, we have an EC2 instance that we are going to use as container host. As I mentioned before, the EC2 service will attach ENI to this instance, and then we'll assign IP addresses to it. Oh, by the way, I'm using an IPv6 address here, and I will be using IPv6 addresses in all of my examples through this presentation. This is because at Netflix, we are committed to migrate to IPv6. We have been working on it for years, and we are still working on it. And there is more benefit to IPv6 that I will mention later in this talk. Back to the setup. This is awesome. So now the EC2 instance, it has the network connectivity. But now we want the containers to also have network connectivity. How do we do that? Know that you can attach more than one ENI to a EC2 instance. So we can attach what we call secondary ENIs. And the secondary ENIs, we can attach security groups to this ENI. And as long as those containers, they share the same security group settings, they can share one secondary ENI. And you can assign multiple IPs to each ENI. In this case, we assign 3 IPs to this ENI, and then we allocate those 3 IPs to the 3 containers respectively. Then now, our job is done. The containers, they have an ENI at layer 2 and IP addresses at layer 3. And in case there are other containers that's using different security group settings, then we need some another secondary ENI, and then we assign IPs to this ENI, and then allocate those to containers respectively. This works, so our job is done here. But not yet. There are some problems to this approach. The first problem is, if you remember, we have an account isolation requirement. And in this case, so actually you see the secondary ENIs, they're in the same account at this EC2 instance. So the network is still in the same account as the EC2 host. But our requirement is some of the applications, they need their network to be in a separate account. The second limit here is we can attach multiple ENIs to an EC2 instance, but there is an upper limit based on the EC2 instance type. For example, on M5 Metal, the instance type we use, Titus uses as a container host, you can attach up to 15 ENIs, and that's 1 primary ENI and 14 secondary ENIs. I mentioned before that the containers, they can share 1 ENI only if they share the same security group settings. In an extreme case, if all of them are using different security group settings, then they can't share any ENIs. So each container needs 1 ENI. So in this case, we can launch at most 14 containers on one M5 Metal. And with 96 CPUs on M5 Metal, we definitely want to run more containers on it. Because of the problems of this option, so we explored option 2, which is called ENI trunking. The idea is simple. So we have the same setup as before, and now we have the same primary ENI here. This time, instead of attaching multiple secondary ENIs, we only attach one secondary ENI, and we call it a trunk ENI. And we have containers running here. We want to assign ENIs and IPs to those containers, and this time we associate some branch ENIs to this trunk ENI. And those branch ENIs, they can be in their own VPC, their own account VPC and subnet. They don't have to be in the same subnet as the EC2 instance. And then we assign IPs to those branch ENIs and then allocate them to those containers respectively. On data plane, we use a technology, Linux technology called IPVLAN. So all the traffic going to the containers, they will first go through the trunk ENI, and then on the trunk ENI, so based on the VLAN information, so each branch ENI maps to one VLAN, and then based on the VLAN and the IP address, we can route the traffic to the container network. Okay, this one works, and also notice that because the branch ENI, they can be in different accounts, so that also meet our account isolation requirement. So next is, speaking of isolation, if you remember, another requirement of isolation is data plane isolation. And I mentioned is we get it for free when we use container runtime like Docker. They have the Linux network namespace that separates the networking from containers. They don't see each other's traffic. But there is still one situation that may make them sense the existence of other containers, and that's the noisy neighbor problem. If you remember, we talked about like all the traffic will go through the trunk ENI first, and then because they share this trunk ENI resource, and there's a bandwidth limit on the trunk ENI, also based on the EC2 instance type. If one container is using too much network, so it may cause packet delay or loss on the trunk ENI, and then impacting other container network traffic. So that's why we need a way to tell those noisy containers to shut up, which means we need some sort of container networking bandwidth limiting or traffic shaping mechanism. At Netflix, we use a traffic shaping algorithm that's called HTB, Hierarchical Token Bucket. We use Linux Traffic Control, or TC tool for that. How it works is on this EC2 instance, we have a trunk ENI, and we attach a root queue disk to this trunk ENI. And queue disk stands for queue discipline. It is a traffic control term. It controls the rate your packet leaves a queue, which in turn controls your throughput. And on this queue disk, we attach a root class, and this class has a bandwidth limit that is the same as the bandwidth limit on the trunk ENI. For each container we launch, we assign a leaf class to each container, and we assign a bandwidth limit to every container. And the sum of all the leaf class bandwidth limit cannot exceed that of the root class, that of the trunk ENI bandwidth limit. As long as we have this setup and we classify the traffic correctly, the Linux TC will just ensure the traffic is shaped, the bandwidth is limited. So for traffic classification, we use a BPF classifier. You can use all kinds of classifier, and we use BPF here. And based on the IP address of those packets, we are going to do the classification, assign the child class or leaf class to those packets so that TC can help us do traffic shaping. All right, so finally, the latency requirement. In order to reduce the network setup latency, we need to understand where is the latency from? What is the bottleneck in the container networking setup? In our experience, the latency comes from AWS API rate limiting. For example, before I mentioned, on each ENI, you can assign multiple IPs to it, and you can call an API called assign private IP addresses to assign those IPs to the branch ENIs. And for each container we launch, each container needs one IP on the network. So for each container, we need to call this IP to assign one IP to this container. So that means the container launching rate is equal to the API calling rate. And at Netflix, the container launching rate is much larger than the limit. Of course, we can ask AWS to increase the limit. They're very nice, they will do it for us, but we can't do that indefinitely. This API is rate limited because it modifies AWS network. So you and me, we both share the same AWS cloud. So they don't want us to modify the network too often because that may impact you guys' network. On AWS cloud, maybe Netflix is the noisy neighbor there, so it is legit for AWS to tell us to shut up. So as a noisy neighbor ourselves, how do we behave ourselves so that we are not penalized by those API rate limiting? Well, again, options. Of course, the idea is because we are calling the API too much, we need to reduce the API cost, and there are several options to do that. One option is we do pre-assign and cache the IPs. If you noticed before, the API we call is called assign private IP addresses. So you can assign multiple IPs for each call. One idea is every time when a container launches, instead of asking for one IP, we ask for 4. Then this way we reduce the API cost to n divided by 4. And we use the one IP for the immediate container, and then we will cache the other 3 that will be used for later containers. But there are problems with this approach. There is something in AWS networking called NAU, or Network Address Unit. This NAU contributes to a total that represents your VPC size. And as you can imagine, there is a limit on this NAU per VPC. Again, at Netflix scale, we are hitting this limit also constantly. And hitting this limit may also mean impacting AWS networking and impact everyone here. And what's more, in order to not use that many NAUs, of course, we need to recycle and use IPs every time we allocate 4. And each IP contributes to 1 NAU in this VPC. Then we want to recycle the unused ones. That makes the implementation a little bit complex. So there's an option 2, that's request batching. The idea is also simple. Because the API is rate limited when we're calling it a lot, and also the API is a batch API, so we can wait for a few seconds. We gather a batch of requests, and then we call the API once. There is no limit on how many IPs you can call within this one API. This time you reduce the API call to n divided by b, where b is the batch size, and it is a dynamic value. This one can also solve the API rate limiting problem. One problem might be because this waiting period is fixed. So even if you don't have a lot of traffic, you don't have a lot of container launching, one container still have to wait for a few seconds for the network to be set up. But because this time is bounded, it is fine to us, it is reasonable. So as you can imagine, so this way we absorb the bursty requests to the API calls. So with a more complex solution and a more simple solution, we definitely chose the simpler one. So if you recognize those 2 patterns from the Netflix show, Squid Game, you will know choosing a simpler pattern here is life-saving. To further reduce the latency, Netflix and AWS, we co-invented a feature called Prefix delegation. We co-invented that here at reInvent in 2019. So far, we have been talking about assigning IPs, assigning the full IP, very specific IP. In terms for IPv6 case, it is /128 IPs, 2 ENIs. The idea of prefix delegation is instead of doing that, we ask AWS to assign a /80 prefix to this ENI. Once we have this prefix assigned to the ENI, we can use all of the IPv6 addresses under the /80. And how many IPs are there? There are 248 IPv6 /128 IP addresses we can use ourselves without talking to AWS again. I mentioned before, I promised you I will talk why we want IPv6 so badly. So this is why. We have a lot of savings. So in theory, you can call AWS API only once, allocating this /80, and then we can launch, in theory, we can launch that many containers without contacting AWS again. Actually, Prefix delegation also support IPv4, but the saving is not as much. IPv4 has a /28 prefix, so that's 224, that's 16 IPs to be saved. So it's definitely not as much as IPv6. We also had, in the previous years of reInvent, we also had talks on IPv6, our IPv6 journey, so feel free to check it out after the talk. In order to harness the power of prefix delegation, we also have something called high-scale network mode. When you launch your container, you can check a box that says high-scale network mode. What it means is your container will be launched in common subnets and using common security groups. I kept mentioning like the containers, they can share ENIs only if they share the same subnet and security groups. That's why by enabling high-scale network mode, we can enable more sharing, so less API calls. And of course, they will be IPv6 only addressing so that they can use IPv6 with prefix delegation. But IPv6 only is not easy. That's why we have been working on it for years. Because even if you are ready to migrate to IPv6 only, some of your dependencies might not be ready yet. So you still need to talk to an endpoint that's IPv4 only. That's why you need some sort of transition mechanism that can translate between IPv6 and IPv4. There are options to that. So one option is to use AWS NAT64 and DNS64. How it works is this. You have an IPv6 only instance container. When it needs to talk to a IPv4 only endpoint, it uses the DNS name of the endpoint, and then you need to contact the DNS resolver, Route 53, to resolve this IPv4 only endpoint DNS name. And the resolver, they will resolve this endpoint to an IPv6 address, a special IPv6 address with a well-known IPv6 prefix, and it embeds the IPv4 address inside this IPv6 address, then return it to the instance. Then the instance will use this IPv6 address to talk to the IPv4 only endpoint. That's not going to work. So that's why the NAT gateway here will also do another translation. It sees this very special, well-known IPv6 prefix, then it's going to convert it back to the embedded IPv4 address, change the packet, and then send this IPv4 packet to the destination, and vice versa on the way back. So this way, the application, the IPv6 only application doesn't need to know about the endpoint being IPv4 and still able to talk to it. Well, at this point, you may already know when I say option one, there are always problems. What are the problems with this approach? So you can guess. First, the DNS resolver is a key here because you need this special IPv6 address. So that means you can only talk to IPv4 only endpoint through DNS names. You cannot use the IP directly. But in some of our use cases, they still need the communication using the IPs directly. Another problem is the NAT gateway does this translation per packet. So that also means your overhead is per packet. With the traffic, the throughput at Netflix, this overhead is not negligible. Last, most importantly, cost, money. You have to pay to use NAT64, DNS64, and with the Netflix scale, the traffic we have to pay millions of dollars in order to use this feature. That's why internally we developed something called TSA, Titus Seccomp agent. This topic was also presented in a Linux Plumber conference in a previous year. Here is a QR code for that presentation. Feel free to check it out after the talk. I won't dive into the details as well, so I will talk about the general idea. So now you have an IPv6 only network container. And when this container application inside this container, they want to talk to an IPv4 only endpoint, they will first create a socket. And inside the Linux kernel, it creates a very simple number user space socket, which maps to an internal representation of this socket. That's a more complex address here. And then you need to call a system call, a connect system call, to connect to this endpoint. If I don't do anything here inside this IPv6 only container, this call will fail. Because there is no IPv4 address here, I cannot communicate with the IPv4 only address. So what we do here is we use Seccomp to intercept this call. And then we also have an IPv4 only transition network namespace. This transition network namespace is a separate namespace from the container network namespace, and it has IPv4 address in it. Inside this IPv4 network namespace, we do another socket call, we get another socket. And we make another connect call, and this call will definitely go through because there is IPv4 address here. Then we will use some seccomp command to replace the Linux internal representation of the original socket with the new IPv4 socket here. Then we return a success to the original caller inside this IPv6 only container. Because the internal representation of this socket is changed, so all the traffic going between the container and the IPv4 only traffic will be sent to the container. Again, the container can talk to IPv4 only endpoint transparently. All right, to recap our requirements and our design. So our first requirement is we want containers to run like VMs. They need one IP on the network, just like EC2. To do that, we have ENI trunking. And we also have isolation requirement, account isolation, and data plane isolation. ENI trunking already meet the account isolation requirement. And on data plane, we have HTTP traffic shaping for us to avoid noisy neighbor problem. And for latency requirement, we have request batching, we have IPv6 with prefix delegation for us. So putting everything together, we built a system that's called IPMan. So IPMan stands for IP management. It is also the name of a Kung Fu master who taught Bruce Lee. So it's a powerful system. Here is the architecture of IPMan. We have an AWS cloud. And we manage what we call Titus agent cluster. And this cluster contains EC2 instances that act as container hosts. On those EC2 instances, we launch containers. And for each container we launch, there is a Titus executor that's responsible for setting up the network for this container. On each EC2 host, we have a IPMan agent. The agent is responsible for network setup, and the IPMan agent will talk to a remote IPMan service cluster for assigning those IPs. Inside each IPMan service cluster, there is a leader service and two followers. The followers are just for failover, and when they receive requests, they will forward those to the leader. And in the case the leader fails, one of the follower will be elected as a leader and then take over. The leader will store its state inside Amazon DynamoDB, and it may talk to AWS EC2 service for assigning ENIs and IPs. As we mentioned before, we want to reduce the latency by reducing those three green arrows here. We want to reduce the cost from the agent to the remote service, as well as the cost from service to AWS EC2 service. So let's walk through an example of IPv6 address assignment here. So for the very first task, it needs an IP, so it talks to the local IPMan agent. The agent doesn't have any state at the moment, so it will call the remote IPMan service asking for an IP. And the service will also doesn't have any state, so it will talk to AWS EC2 service looking for an ENI with a /80 IPv6 address. AWS EC2 service will allocate such an ENI with this IPv6 prefix, and then return it back to IPMan service. The service then returns this to the agent. The agent now has the state. It knows I can use this ENI. This ENI has an IP prefix, and I can use any IP under this prefix. So it finds the first available one, ::1, and allocate that to this task. And it will save the state locally. Then, for all following tasks, they are going to talk to the agent and the agent only. So the agent now already has this state. It knows I have this ENI to be used. It has this /80 prefix. ::1 is already used by task 1, so I'm going to assign the next available ::2 to the task 2. This way, we only call AWS once, and this is second task, third, fourth, everything. So we only call AWS once. So now you might think, well, this is great, this is fantastic. So, but on paper, how does it really work in reality in production? Let's take a look at some of the metrics we collect in production. So at one point, we were running 800 containers per second, and that's millions of containers per day. At this rate, with IPv6 only network setup latency, we can achieve 100 milliseconds P99 latency for network setup. This is IPv6, of course, which can benefit from prefix delegation, which is the main contributor of reducing latency. Overall, the latency, the P99 latency is 4 seconds. And this is because of request batching. And sometimes we still hit the AWS API rate limiting because not everyone is on IPv6 yet. We are still working on migrating everyone to IPv6. In fact, we use this as an incentive to encourage people to move to IPv6. Basically, if you're still using IPv4, then your container will take longer to launch compared to those using IPv6 only. All right, so now our job is done here, right? We have an efficient way to configure the container networking for millions of containers. That's the topic today. So why do I still have a job at Netflix? What's next? The short answer is we want to be more efficient. Number one thing is, as I kept mentioning, IPv6 migration. We want everyone to benefit from prefix delegation. We want to continue our IPv6 migration so that the overall network P99 setup latency can be brought down. Another thing I didn't mention before when I talked about HTTP traffic shaping is when the packet per second rate is high, we sometimes experience performance issue due to some global lock in the HTTP implementation that's out of our control. So we were also looking for a more performant traffic shaping mechanism. Another thing I didn't mention is when I talked about IPVLAN on the data plane. So the packet, in order to use IPVLAN, the packet, each network packet has to go through the Linux network TCP stack twice. One is on the host, one is inside the container network namespace. So because of that, your container networking is not going to be as performant as EC2 network. It's not very bad, but it's still not as performant. So we would like to explore other ways to reduce this one extra layer of TCP stack traversal. Linux kernel had some new feature called Netkit that can potentially solve this problem, and we were exploring this option. All right, so these are all my topics today. So I hope you enjoyed the talk. And for those of you who switched to watch Netflix in the middle, I hope you enjoyed the show. So thank you all for attending. And I don't know if we have Q&A session, but I can stay here for a while in case you have questions. Thank you.